Hi! In our last video, we saw how to express a head versus Q curve of a pump as a second-degree polynomial expression. We used the least squares method for this purpose. Then, we put together the pump and the system expressions and found the operating point for which there is a flow and a head. Here is the operating point of our system. We marked it in the pump chart, and thus we obtain the corresponding values for the required NPSH and BHP. But we can find these values from expressions that we can obtain from these curves, just like we did for the H versus Q curve. Let's start with the BHP curve. We select some values of Q and transform them from cubic meters per hour to liters per second. Here are the corresponding values of P. Then we bring the values of Q and P to this table, calculate the values of the columns and their sums, like we did for the flow in our last video. We calculate the values of the determinants delta, delta A, delta B, and delta C for the Cramer's rule. With their values, we calculate A, B, and C. Here's the equation for the BHP. See in the figure how the function that we found is close to the curve from the pump chart. The procedure for the NPSHr is just the same. We take these pairs of values from the curve, bring them to this table, calculate the values of the determinants delta, delta A, delta B, and delta C, which allows us to calculate A, B, and C. Here is the equation for the NPSHr curve. See in the figure how the function that we found is close to the curve from the pump chart. Okay, the last one. It's for the efficiency of the pump. We take these pairs of values, bring them to this table, calculate the values of the determinants delta, delta A, delta B, and delta C, which allows us to calculate A, B, and C. Here's the equation for the efficiency curve. See in the figure how the function that we found is close to the curve from the pump chart. Okay, the plan is to substitute the graphical procedure method by algebraic procedure method. For this, we have second-degree polynomial expressions for H versus Q, power versus Q, required NPSH versus Q, and efficiency versus Q. They will spare us a lot of work. For example, if we want to know the pump efficiency, we have to mark the operating point in the pump chart and read it by approximation. It's between 70 and 75%. Could it be 74%? Or we can use the efficiency equation and find that it is 74.1%. Now, this is what we gotta do to find the power. We trace a vertical line from the operating point to the BHP curve and find 6 HP, maybe a little more, I'm not sure. But if we use the BHP equation, we just substitute the values and find 6.4 HP. And now the last one. This is what we have to do to find the required NPSH. We trace a vertical line from the operating point to the corresponding curve and find 0.8 meter. But if we use the NPSH equation, we just substitute the values and find 0.83 meters. Here are the values that we find by referring to the pump chart and the values that we found with our functions. Not bad, what do you think? Now we're able to solve problems in which we'll associate pumps, systems, modify the speed of the pumps, and the diameters of their impellers, As you can see, there's a lot of new videos coming on. Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.